and I work at Murex as a lead developer of a C++ software team. Today, we're going to talk about the STL algorithms, which is a fantastic topic. Well, I'm going to start with a question to you. Who is aware that it's a good thing to know the STL algorithms? Who's aware of that fact? That's pretty much every hand raising. Now, who knows them, each and every one of them? Raise a hand. That's none of hands. That's exactly the point of that talk. When you walk out of that room, you will know every STL algorithm there is in the library as of C++ 17. The agenda will follow, it's starting by talking about what is exactly an STL algorithm, why it's so important and what they can bring to us, and then we'll get to the actual algorithms in an entertaining way, I hope, and that second bit will take less than an hour. All right? Let's dive in. So what's an algorithm in the STL? An algorithm is a function that operates on a collection. In the design of the STL, it doesn't have access to the collection itself, but it accesses it through iterators that the collection provides. This allows collection to be a wide variety of things. It can be a vector, for example, that provides iterators. In this example, for each is one STL algorithm that uses those iterators. It can be any STL container, like set or map or array. It can be an old array, or it can be an older array, or it can be something complicated like streams, or it can be your collection. Like if you design a custom class that represents a collection, it's a good thing to make it expose some iterators, at least a beginning and end, to be able to use the power of the STL algorithms. In the future, the interface that algorithms will use will likely be different. It will be ranges, which provide iterators, but the algorithm will talk to the range. A range is something that can be iterated over, and for that reason, every STL container is a range, and that will lead to simpler code. Using iterators is more powerful because it gives you more flexibility to iterate on a subpart of a collection, but in most cases, you just want to treat the whole collection, and range is just fine. This is the future of the STL. Today, we're going to talk about the present of the STL, but I just wanted to mention that. And all the code example will use iterators, but that will be the same idea with ranges. Now, so there's a fact that's been popularized across the C++ community over the past couple of years, is that we need to know all the STL algorithms. We need to know them well, very well. But why? For several reasons. One reason is that it makes our code simpler, and sometimes it's spectacular. We've already seen that talk from Sean Parent a couple of years ago, who transformed a big chunk of code into a very small and expressive piece of code just by choosing the algorithms correctly. Now, there are other reasons. One of them is that the algorithms work, and they don't fall into some traps that we could fall into while writing our own code that manipulate collections with for loops. One trap we can fall into is doing something wrong in the iteration and going past the end of a collection. If we do some sort of complicated traversal of a collection with a for loop. And if we do that, we get into the realm of undefined behavior. And from this point on, anything could happen. Literally, anything could happen. What's happening on the screen right now is completely standard C++ if you walk past the end of a collection. Another kind of mistake is to do something wrong with an empty loop. Every time we write a loop, we have to think about the case where there's nothing in the collection, and we have to do that mental check and run that risk of having that wrong. And if we get that wrong, it's undefined behavior all over again. Other kind of mistakes we can make is about complexity. Some algorithms have several possible implementations. Some of them are more astute than others and can get a better complexity. We'll get into more details about that later, but for example, algorithms on sets can be implemented naively in a quadratic complexity and with more work in linear complexity. STL algorithms have an optimal, whatever that means, complexity. They're used by billions of people every day. Right, maybe not billions of people every day, but they're used by a lot of people very often. So, so they're thoroughly tested and they work. They are a great tool to make our code more expressive because they allow to rise the level of abstraction. And to me, this is one of the major things that can make code more expressive. By raising abstraction, I mean telling what we want to do as opposed to how we want it executed. Also, they are part of the common vocabulary of C++ developers. It's something that is standard, so you can use it. You can use it without fear of someone not knowing them. I think that we have to level up to the algorithms and not the other way around, and that's what we're going to do today by seeing them all. All algorithms are standard, and you can use all of them, whatever your version, your current version of C++. Some new algorithms have appeared in C++ 11 and C++ 17, and even if you don't have C++ 11 or C++ 17, for most of them, you can use them just by going on the internet on cppreference.com, for example, copy-pasting their implementation into your code, and off you go. So you can use pretty much all of them, regardless of your current version of C++. Now, to learn them, there are several things we can do. One of them is to actually know what's in that library, which is the topic of today. But to go further, it's a good thing to understand their technical aspects, like their complexity, or their prerequisite, post-requisite, like some takes sorted collections, for example. And it's also a good thing to see what's inside them, like see how they're implemented. Once we get familiar with that library, it sort of comes off on our coding style. We get inspired. We get a feel for what good abstractions look like. And we can design our abstraction better by being familiar with the STL. And once we're familiar enough, then we can write our own algorithms, and we'll touch upon that at the end of the presentation. Now, there's a trap that lies right at the beginning of the path to the STL algorithms. And this trap is called for each. For each is one of the STL algorithms. There's nothing wrong about it in itself, but the thing is, it looks like a for loop. So if you want to change your for loops into algorithms, you may be tempted to use for each, replace a for loop by a for each, and think that you've done it like using STL algorithms. And it wouldn't be quite right, because there's much more than for each in the STL algorithms library. And a lot of other algorithms can let you write your code with more nuance. I'm going to show you something to illustrate that there is much more than for each in the STL library. Ladies and gentlemen, I present to you the world of the STL algorithms, the way I see it. In this world, I've mapped out all the algorithms there is in the library. Every algorithm is a city, and I've grouped them by theme and how they relate to each other. And that's the most efficient way I know to retain them and actually go out and look for them and use them in code on an everyday basis. We're going to explore that world, and that's what we're going to do for the rest of the presentation. Before we actually dive in, though, we can make some observation about looking at it from afar. One observation is that for each is just one of them lost on an island. Another observation is where most algorithms lie. I would have thought that most algorithms would modify a collection one way or another, like sort or partition or whatever. But actually, most of them live in this region, which is called the land of queries, because they all go out and retrieve a piece of information on a collection. They don't modify it. So most algorithms don't modify the collections, just go and get a piece of information for you. I suggest that we begin our journey by exploring the other end of the world from for each, which is the algorithms on heaps. So algorithms on heaps work on heaps. So what is a heap to begin with? A heap is a data structure that can be represented in the form of a tree where there's a property, it's called a heap property, where every node is smaller than its children. I think it's called a heap because when you make a heap in real life, you'd better have the small one at the top. In the heap on the right, you can observe that it's the other way around. Every node is bigger than their children. That's how C++ make heaps. It's a max heap. So it's not like real life, but I think that developers don't really live in the real life anyway. So does it really matter? I don't think so. So a heap can be represented in the form of a tree. Now, to use it with the STL algorithm, we need somehow a beginning and an end. To do that, we represent that tree into an array. Let me do that just one more time, more slowly. To represent a heap or any binary tree in an array, we take the first row, which is the root of the tree, and then the second row, and then the third, and so on and so forth. And when we do this, there's a nice property that is to go from one node to its left child, it's essentially multiplying its index by 2, essentially. So we now have an array representation of a heap. OK, so the first thing we can think of is imagine that we've got a collection, which is not a heap because it doesn't respect the heap property, and we'd like to make it a heap. To do that, to make it a heap, we call make heap, which is our first STL algorithm of today. Make heap takes a collection, beginning and end, and reorders it to make it a heap. Now, to add something to a heap, in general, independently of C++, to add something to a heap, we just put it at the end, the new thing. It's probably not at the right position, so we're going to make it bubble up its way through the tree until it reaches its final position, so we swap it with its father whenever it doesn't respect the heap property. To do that with the STL, so let's put it back into an array structure. We can just add it to the end of the array, so that we're using a vector, for example, so we call pushback. And then to make it bubble its way up through the tree, there's this algorithm, which is called push heap, that takes the last element of the collection and makes it bubble up its way through its final position. If we think of it in terms of a heap of a tree, that's how it would look like. Now, to remove something from a heap, well, the point of a heap, actually, is to be able to get the largest element in a max heap in constant time, because that's the root of the tree or the first element of the vector. To remove something from a heap, we can only remove this largest element. So how to remove it? We call pop heap, which starts by putting it at the end and putting the last element at its position. And the last element, which is probably one of the smallest ones, because it's at the bottom of the tree. It's not at the correct position at the top. So pop heap is going to make it bubble its way down through the tree to its final position. And then we just pop it back. Now, if we don't pop it back, if we just repeatedly call push heap on the shrinking tree, on the shrinking heap, then you can imagine that the current biggest element is going to go at the end of the shrinking heap. And if you do that repeatedly until there's no heap left, you're going to get a sorted collection. Can everyone see that? I see you nodding, OK. This is what sort heap does, stood sort heap. Stood sort heap lives on a border between the region of heaps and the shore of sorting, which leads us to the shore of sorting. So how do we sort stuff in C++ with the STL? Well, to sort a collection, the simplest way, the way that takes the least characters, is sort. So stood sort just sorts a collection. OK. Now, there's much more to it than stood sort when it comes to sorting with the STL. We can sort only a subset of the collection if we don't need it completely sorted. To sort, say, just the beginning of the collection, we call partial sort. So partial sort takes a beginning and an end, and also an iterator that points to somewhere in the collection, and sorts only the beginning of the collection. And the rest is bigger. It's not smaller than what's on the left of that position, but it's not particularly sorted. Right? That's partial sort. Now we can do it even more targeted by sorting just one element, which is done with nth element. So with nth element, you pass an iterator that points to one position where you want the element that would have been there if the whole collection was sorted. So this guy goes there, and the rest is not particularly sorted, other than that the element on the left of the nth are going to be smaller, and the element on the right are going to be not smaller. All right? There is sort heap, which we've talked about. And finally, there's in-place merge, which makes a merge sort. It's the incremental step in merge sort. So in-place merge takes a collection that has the prerequisite of having two parts which are sorted. Both are sorted, but the whole thing is not sorted. Well, in-place merge makes the whole thing sorted. And that's it for sorting. If we go just near them, we get to partitioning. Partitioning is about looking at a collection with a predicate, saying being blue for that collection, for example, and putting all the blue ones at the beginning and the not blue ones at the end. That works with any predicate and not just with being blue. Stood partition, every algorithm lives in the stood namespace. Stood partition does just that. And the position which is kind of like in the middle, the end of the blue section and the begin of the white section is called the partition point. And there's an algorithm that retrieves the partition point of a partitioned collection, and it's called stood partition point. If we take a step back, we've been traveling around the land of permutations, which are algorithms that change the order of the elements of a collection without changing their values. There are a couple left, like those guys, which we're going to see now. So rotate has become quite popular over the past few years. It's a cyclic permutation. So the one at the end goes to the beginning. Potentially, several ones at the end go at the beginning. Now, another way to to make a permutation is to make it at random, which is what shuffle does. Shuffle takes a random generator and reorganizes a collection randomly. Now there's an order on permutations. Like you can say this permutation is smaller than that permutation for a given collection. And to get a feel for that order, it's like an alphabetical order. It's lexicographical order. It's like in a dictionary, right? Like comparing words. So if you think about words with letters, you see how a word is before another one in the dictionary. It comes from the fact that you can compare letters. So if you can compare the elements of the collection that constitute its letters, then you can define an order of permutations. And next permutations allows to traverse this set of permutations. So if you call next permutation begin end on a collection, it's going to reorder it so that it goes to the permutation which is just after the one that it was currently in. And when it gets at the end of this order, it rolls over to the beginning. That's next permutation, and prev permutation goes back. This is useful if you want to do something for every permutation of a collection. And the last one, which is probably the simplest one, is reverse, which reverses a collection. There's this one, which we haven't talked about, random shuffle, because it's a rec, which means it has been deprecated, and shuffle replaces it since C++11, so we should use shuffle. Now there's this part of the map that's on the corner, and which I call the runes. It's those things that you can combine with algorithms to make new algorithms, like stable or if. I call them that because it's like there's an algorithm that goes to a rune that has a magical power that can augment it somehow, and I also call them that because I find that cool. With the algorithms we've seen so far, there are some runes that we can understand now, like the stable one. Stable means that the relative order of elements doesn't change after the transformation. For example, in a partition, you get all the blue ones at the beginning for sure, but perhaps that some of the blue ones have been changed in order. With stable partition, it doesn't happen. They keep their relative order for more algorithmic complexity, of course. There is the is rune, which checks for a property. So now we know what sorted, partition, and heap mean. Is heap, for example, takes a collection, a begin and an end, and returns a Boolean to say whether this collection is a heap, respects a heap property, and so on for sorted and partitioned. And there's a variant which is called is sorted until, which returns an iterator to the first position where that property is no longer true. In the particular case of a sorted collection, a sorted until returns the end of collection. All right, so we've been around all the lands of permutations down there. Now let's get into the big part of the world, the land of queries, which stretches out all in this region. And zooming in, we can see that there are several sorts of queries. The queries that return a value, or the queries that do research, that search a value in the collection, and some others. We're going to go through all of them. That won't take that much time. Let's start with a value, the algorithms that return a value. Well, the simplest one is probably count. That takes collection, begin end, and a value, and returns the number of times that value occurs in the collection. So in that example, count of x returns 3. Accumulate makes the sum of the element in a collection and returns it. Or custom operations to replace the operator plus. Now, in C++17, there have been reduce and transform reduce that have been added to the standards that do pretty much the same as accumulate. Reduce does the same, except that it has another overload that doesn't take an initial value, which is cool, and can also be parallelized, which is cool as well. And transform reduce is like reduce, except that it applies a function on the values of the collection before calling reduce. So transform reduce takes a function, or a template, function, object, whatever, and applies it before calling reduce. Partial sum, makes a partial sum, which means that the first element stays the same, the second one is equal to the first one plus the second one. In position 3, we've got 1 plus 2 plus 3, and then 1 plus 3 plus 2 plus 3 plus 4, and so on. Get it, right? There's inclusive scan, exclusive scan, transform, inclusive scan, transform, exclusive scan, coming in C++17, which do pretty much the same as partial sum. Exclusive scan does the same, but it can be parallelized. And that's inclusive scan that does the same, but can be parallelized. But exclusive scan makes the partial sum of the value up until one position, but without including it. So, for example, the first one stays the same. The second one is equal to the first one. The third one is the first one plus the second one. The fourth is 1 plus 2 plus 3, right? So that's exclusive scan because it excludes the current one. And transform, either inclusive or exclusive, is like transform reduce and applies a function before performing the exclusive or inclusive scan. Inner product makes the inner product, which means that it multiplies the element of two collections 2 by 2 and sums the results. And adjacent difference makes the difference of every neighbor in the collection. So the second one becomes the 2 minus 1, the third way becomes 3 minus 2, and so on and so forth. And finally, sample picks out a few elements from a collection randomly. So you give it how many elements you want from the collection, you give it a random generator, and it will pick out some elements for you. That was for querying a value. Now we can query a property. So what kind of property can we query? Those guys are extremely useful on a day-to-day basis. They use it very often. So Olive takes a collection, big and end, and a predicate, and returns a Boolean that says whether that collection, all the elements of that collection satisfy the predicate. Any of takes a collection and a predicate and returns whether at least one of them is satisfy the predicates, and none of returns a Boolean saying if whether none of them satisfy the predicate. Now we can wonder what happens if we pass an empty collection to Olive. What do you think? There are only 2 possible answers, so you've got 50% chances of getting it right. Yeah, that's true. It's true. Or you can think of it when you compare it to maths, as in for everything in the empty set, whatever follows is true. Or you can think of it as a convention, but it's good to know. Now, what if we pass an empty range to any of? What does it return? True? False? One of you is right. That's false, because it's not true that there's at least one that satisfies the predicate. And what if we pass an empty collection to none of? That's true. Now, that was properties on one range. We can also query a property on 2 ranges. The first one, the idea is to somehow compare 2 ranges. So the first one says, expresses whether those ranges contain the same contents. So every element, all elements are equal and in the same order and have the collection have the same size, and that returns a Boolean. Now, if we only want to know if this is the same contents but not necessarily in the same order, there is permutation, returning a Boolean as well. Now, we can compare two ranges to say which one is smaller. And it's not about size, it's more precise than that. So it comes back again to comparing like in the dictionary, right? So we can imagine how words are smaller than each other. Well, in this example with chars, we can easily see that the first one is smaller, right, than the second one. It also works with any element that has a less than operator, and that returns a Boolean. And the final one in this two ranges property querying is mismatch. So mismatch scans two collections and stops when it finds a difference. And what it does, it returns the position when they start to differ with a pair of iterators. And finally, in the not finally, now in the land of research, so research works in two ways, essentially. It depends on whether the collection you're searching into is sorted or not sorted, because you don't search the same way, obviously. Well, let's start with the not sorted, because not so many in them. So if you want to find something, you just call did find, which a lot of people know already and use. Now, there's one that's a bit less famous, but quite useful. It's when you're looking for two consecutive occurrences of a value. Like, I want to find the place where two orange appear in a row, and that's adjacent find. Now, for the sorted part of the region of the search in the world, to find a value, well, if we're looking for a value like orange, for example, there may be several occurrences, but contrary to the not sorted part, they're going to be together, right? Because it's sorted. So the place where the orange value lie is a range. It's a subrange of a collection. That could be empty if there's no orange at all, but that's a subrange which you can get with equal range. And that's how we search a sorted collection for a value. Now, there are other algorithms that are related to searching, like lower bound and upper bound. But those guys, you can use them to find a position, like what would be the position to insert an orange value on the left of the potentially existing orange values. That's lower bound. And upper bound is on the right of the potentially existing lower values, but orange values. But if there's no orange value in this collection, lower bound is not going to return end like find does, right? So to search in a sorted collection, that's equal range. And there's this guy, binary search, that performs a binary search, luckily, but it wouldn't tell you where it found the value you're searching for. It only gives you a Boolean that says whether it is there or not. Now, that was searching for a value. Now we can search for a range. A small range is inside of a big range with this algorithm that has an unfortunate name because it's called search, which looks very much like find, but doesn't mean the same thing at all, because search is for a range inside of a range. Search gives you the first occurrence of the small range. Now, to get the last occurrence, it's an algorithm that has an even more unfortunate name, because it's called find end. That's right. And if you want to search for the first occurrence of any of the values of the small subrange to the big one, that's find first of. And last section in the queries, that's how to find a relative value of the bigger one and the smaller one. Well, the bigger one is with max element that returns an iterator with the position of the biggest element in the collection, and min element, the smallest one. And if you want both at the same time in one pass, that's min-max element. That returns a pair of iterators. Right, that's it for the land of queries, which was the biggest part of the world. Now we're going to move on, my favorite part of the world, the glorious quantity of algorithms and sets. They are glorious. So what's a set to begin with? A set in C++ is a sorted collection. It can be a std set, which is sorted, but it can also be a sorted vector, for example. Now, there are operations we can make on sets that looks like mathematical operations on sets, like getting the difference between two sets. Like, I've got a set A and a set B, and I want the elements that are in A but not in B, and the two collections are sorted, then we call set difference. And this has linear complexity, whereas if we had a naive implementation that would just pick the first one in A and look for it in B, and so on and so forth, that would be quadratic. This is my favorite algorithm. It has siblings, like set intersection, set union, set symmetric difference, which has a long name. Includes that returns a Boolean to say whether all the elements of B are in A, and merge, that takes two sorted collections and returns one sorted collection that contains all the elements from both. These guys are extremely useful, in particular set difference. That's it. That went really fast. OK, let's take a step back. So we've been through lands of permutation, land of queries, and algorithms and sets, which are the biggest regions in the world. So we now have this part of the world to explore left, and we'll be over. So let's start with this side of the world, the movers that move things around. So the simplest way to move stuff is to copy it somewhere else. Right? That's maybe the simplest algorithms in the whole library. The simplest algorithm, it's copy, and it takes a beginning and end, and output iterators and copies successively every element from the input range. It could do a global mem move under certain conditions. Now, if you like to move, actually move, as in like in a std move, the element from the input to the output, well, there's an algorithm that's called std move. We all know std move, as in like the normal std move, but this guy is less famous and does a move on the whole collection, every element in a collection. Now, to swap two collections that have the same size, that's swap ranges. Let's make a little exercise. Let's say that we've got a collection, which is the one above, 1 through 10, and we'd like to do something to make it reach the state at the bottom. So copy all the subrange starting from 1 going to 5, 4 positions out. What algorithm do you think we can use? There is about 105 possible answers, so there is a high probability of getting that wrong if you pick a random. What's that? Yeah, std copy. That's what I was thinking as well. So let's start with std copy. So std copy starts by copying the first element to the output, and oops, we've lost 4. So maybe we could start from the end, like starting by copying this one on a position that we don't care about because we want to override it anyway, and then the one before, and then the one before, and so on, until the beginning of the collection. So we'd need a way to copy backwards, right? So we can use copy backwards. And there's also move backwards. That doesn't copy, but moves. That's it for movers. Just around the corner are the scarce land of the value modifiers, which I would have thought would be in majority, but the majority of our queries. There are algorithms that modify the values. Those guys, we're going to see them just now, but not so many of them. So fill takes a collection and value and fills that collection with that value, right? Generate takes a collection and a function. It does pretty much the same thing as fill, except that the value comes from the function. So it's a function that can be called with no arguments, and it would call it for every element and retrieve that value and put it in the collection. IOTA, which has a funny name, takes a value, put it at the beginning, and increments it to fill the whole collection with incremental value, right? And replace, which is the simplest one, well, it replaces a value by another value. So in a collection, to replace a collection with 42 by 43 will change every 42 into a 43 in the collection. Right? Just further down, there is this island of structure changes. By structure changes, I mean that the collection doesn't look the same from afar after you've called that kind of algorithm. They essentially remove stuff from the collection. So to remove something from a vector, for example, we call remove, but it's not as simple as that. So remove is an algorithm, and like we saw at the very beginning, it doesn't have access to the collection. It only can speak with iterators. So the best it can do is to change the value inside of a collection. So this is what it's going to do by shifting up the remaining values that we don't want to remove. So we want to remove all the, let me do that again. We want to remove the 99. We're going to shove up all the values that are not 99. And those values that are left at the end are unspecified. We can't count on what's in there. Now we need to do something to actually remove that from the vector, for example. And so we'd like to erase a subrange starting from this position, which is returned by remove, and until the end of the collection. Which is a mouthful for just saying remove 99, isn't it? So I suggest that you just wrap that into a nice function that says remove stuff, right? There's been a proposal to include that in the standards, so it really makes code simpler. I mean, it makes code normal because that one is complicated. To remove duplicates, we'd call unique, and note that unique only remove the adjacent duplicate. So here, I've got 399 in a row, and the last two are going to be removed, but this one at the end won't be removed because unique makes a linear traversal, right? And other than that, it works the same as remove by returning an iterator that we can use to erase and wrap that into a free function. We've unlocked a rune, copy, because we've seen all the algorithms that are combined with copy in the library. So copy is doing the same thing as the algorithm, except that it doesn't do it on the collection. It's a read-only algorithm and takes output iterators to output the results somewhere else. We've unlocked if. That takes a predicate instead of a value. So findIf takes a predicate and finds the first value that satisfies that predicate and not equal to that value. And we can move along to the lonely islands we started with at the beginning, where for each lives and transform as well. I couldn't quite fit them into a family, although they're useful. So let's start with transform. Transform applies a function on every element of a collection, right? It's as simple as that. And it has an output iterator, so the output is probably somewhere else, or it can be the begin of that collection if you want to do that in place. One thing that's a bit less famous about transform that's quite useful is its other overload, which takes two input collections and a function that takes two parameters, right? Like plus, for example, if you'd like to sum the values 2 by 2 of two collections and put that somewhere, that transform allows you to do that in one line of code. And for each, the famous one, well, for each does a very simple thing. If you call for each with the function f on your collection, it's going to call f on that, on every element. and not care about what f returns. So f might as well return void. Now, what do you think would happen with a function that returns void? It starts with an S and then an I. It's side effects. A function that returns void probably does side effects. So for each does side effects. It's made for doing side effects and not for replacing for loops in general. Now, this is not necessarily a bad thing. I'm not saying that side effects are bad. I'm just saying that for each is for side effects. Alrighty. So let's take a step back. So we've been literally all around the world except for this place, raw memory. So let's finish with that. What is that? Raw memory. Remember fill, copy, and move. They have something in common. What they have in common is that they call the assignment operator. Now, to call the assignment operator on something, you're assuming that its constructor has been called, and hopefully you're right. Now, in some cases, you've got a chunk of memory coming from somewhere, shared memory or the OS or wherever. You've got just a chunk of an initialized memory, and you can't call fill, copy, or move on them because you can't call operator equal on something that hasn't been constructed yet. So you'd need something to do that, but with the constructor, and that's what the uninitialized algorithms do. So an initialized fill call the constructor that takes 42 in our example. Copy uses a copy constructor and move the move constructor. So imagine you've got a chunk of memory coming from somewhere, raw memory. You can initialize it with 42s if you use initialized fill with the beginning and the end, which are marked by pointers, right? Now, when you've finished using this collection, you call the destructor of every element with destroy with a beginning and end that calls the destructor successively of every element in that piece of memory, leaving it initialized and ready to be handed back to whoever passed it on to you. There are other options, like to call the default construction or the value construction with initialized default construct and value construct. We've unlocked the final rune, underscore n. So underscore n is a slight variation of an interface. Take fill n, for example. If you remember fill, the interface of fill, it was taking a beginning and an end, like everyone pretty much, and a value. Now, fill n takes a begin and a size, and will do the same thing as fill, except it will do it from begin to 5 steps further down. Does that make sense? Right. Now, what do you think this does? Imagine I've got a collection that is a vector which is empty. What does this line do, in your opinion? So it's going to put a 42 5 times, starting from this iterator. And when you pass something to this iterator, it pushes back that value into the collection that it's bound to. So we're going to end up with a vector that contains 5 times the value 42. Make sense? All right. OK, so we've been all over the world of the STL algorithms. You know every algorithm in the library now. Now what? Well, first of all, you can use them, obviously. You can use them to make your code simpler, to replace your for loops or to not write for loops in the first place. And if you have a case that you're not sure about what algorithm to use and you have a feeling that you can use an algorithm, I'm happy to have a look. Just reach out to me. Use them to make your code more expressive. Knowing them, now that you know them, you can understand that common vocabulary, and you can use that common vocabulary to express your intention precisely. If you like more than the STL, there are other algorithms living somewhere else, like in Boost, for example. They're scattered across the libraries of Boost. Most of them are in the Boost algorithms, but some of them are somewhere else in Boost. And I encourage you to actually go and look for their technical aspects, like algorithmic complexity, which we've briefly touched upon with set algorithms, prerequisite, postrequisites, and look at the implementation. It's really, really instructive. And once you've been familiar enough, get inspired, get a feeling for what good abstractions are to write for your own code. And when you're familiar enough, you can start thinking about writing your own algorithm. So what sort of algorithm would you write? Well, you could do a simple thing and combine an existing algorithm with a rune to create a combination that doesn't exist yet, like sort copy, for example. Or you could add a city, enrich a family, right? If I had to add one, I think I'd add something in the algorithms on sets, which I love so much. I'd add something that would take two sets and return what's in A not in B, what's in both, and what's in B not in A in a single pass. That's one thing we could add to the algorithms. Or you could start a family. If you'd like to get the map, you can just go on fluencypp.com/getthemap, where you can download it, or you could get a poster of the map to hang it in your office or at home, which is lovely. And for the people in the room, I've got a bunch of them here. If you're interested to go home with a souvenir, just come and see me after the talk. Other than that, if you'd like to chat about the STL or about things or whatever, you can reach out to me on Twitter and stay connected, or find me on Fluency++. Thank you.